if there was an opportunity for me to talk about generative, models and Bayes, that was going to be today, because I am super excited about this latest paper of mine and my students, Yueshi Wang's, and I would like to tell you about essentially performing Bayesian simulation when the likelihood is not available. So it's essentially kind of a simulator based a simulation based approach to Bayesian inference without the likelihood. So the work is based on a collaboration with my student Yueshi Wang, who is now graduating, and we used adversarial techniques. So the original title of my talk was Adversarial Bayesian Simulation, but I think that that's a little bit too adversarial for some audiences. So I changed it to Generative AI for Bayes. But the whole idea is essentially using adversarial techniques where we have two agents, two machines playing a game. And in the context of adversarial learning or generative adversarial networks, you may be familiar with the terminology generator and critic. So in this work, I like to think of Yueshi as the generator and me as the critic. And whenever a generator and critic play a game, good things happen at the equilibrium. And in this case, we will be able to simulate from a approximate posterior at the equilibrium, and that's the endpoint of the game. Okay, so I would like to put my work in the context of likelihood-free inference. So we have data, which does not necessarily have to be independent, but it's realized from some model, which is underpinned by a parameter theta naught that we want to learn about. And as Bayesians, we will be assigning a prior distribution, and we will learn about theta naught from a posterior distribution. So the posterior object here obviously depends on the prior, right, and on the likelihood function. And we will be focusing on the situations where the likelihood function either cannot be easily evaluated for each theta, or is just not necessarily available in a tractable form. So such situations happen very often when we have, for example, hierarchical models where integrating over latent variables, the integration is not yielding tractable expressions. So those situations happen very often. I'm also listing some examples from finance. For example, the Heston model. That model is defined by sort of stochastic, a process, continuous time process, and in reality, we obtain discretization. And being able to kind of evaluate the likelihood is also very, very challenging in these types of models. So likelihood-free, or at least models where the likelihood function is not available, those are very prevalent. So I like to think that sooner or later in your careers, you will come across a model where the likelihood is not tractable. And we want to do Bayesian inference. Okay, so the traditional approach to likelihood-free Bayesian inference is using ABC techniques, approximate Bayesian computation. So what ABC does, it compares the data that you observe against data that you generate from the likelihood. So the underlying assumption here is that the likelihood cannot be easily evaluated, but it can be easily simulated from. So for each parameter value, if we are able to simulate fake data, right, from the likelihood, if that fake data resembles the true observed data, then it's possible that the underlying parameter value is close to the true value theta naught. So that's the underlying intuition. So what ABC essentially does is it generates a series of fake data sets. And these are joint data sets where we simulate first from a prior, so theta from a prior, and then we generate X theta from the likelihood. And sometimes it happens that the data will be close to the observed data, in which case we may choose to keep the parameter value theta. And if the observed data is too far, then we discard the parameter theta. So we essentially perform a filtering mechanism where we only keep the sample parameter values that have yielded fake data that are indistinguishable from the observed data. So this process essentially requires generating large, we call them reference tables. So these samples with the joint likelihood, typically we have to simulate many times in order to obtain only a few samples for which the fake data was close enough. So it is a quite elaborate or maybe involved simulation. However, it can be done in parallel, so there are definitely some computational advantages. And I also like to think that conceptually it's a really compelling idea to be able to compare aspects of fake and real data. And that's what also underlies a lot of the adversarial generative networks. So when working on sort of looking into ABC, I wanted to understand how can we actually turn some of these generative network simulators into posterior simulators, and that's the whole sort of underlying motivation for this work. So ABC is not necessarily adversarial technique, right? But it has aspects of adversarial aspects, because we are comparing aspects of fake and real data. We first compress the data into summary statistics, and then if the summary statistics are close, then we consider the two data sets to be similar. So choosing summary statistics is a challenge. ABC may not be great for model comparisons and so on, but it is nevertheless a widely popular technique. So what we have done in one of our previous papers is we essentially replaced the comparison of summary statistics with the classification step. This was suggested earlier by Gutman and co-authors who sort of use classifiers for comparing fake and real data. So we essentially use a classification-based estimator of the KL divergence, and we compare the fake and real data using the estimate of the KL divergence. And there are many other techniques using persisting distances and so on. I don't want to be exhaustive here, but the literature is quite rich. So ABC is a very interesting approach. It's not the only approach for likelihood-free Bayesian inference. I would like to also highlight contributions in the sort of sequential sampling literature. So the Metropolis-Hastings algorithm is one of the kind of basic algorithms, one of the most widely used algorithms, and it's based on the idea of comparing posterior ratios, right, of the current step or current location of the parameter and then the proposed location of the parameter. So it requires the likelihood, right? It evaluates the likelihood ratio. If that's not available, we can replace it with an estimator. We could either construct a sort of likelihood for summary statistics of the data. This yields to synthetic likelihood approaches, or we could replace it with some estimator of the likelihood ratio or likelihood itself. So this yields to other techniques which have received a lot of attention. One of the problems with these types of techniques is that sometimes you may not be able to obtain the correct stationary distribution. That's not automatic, but sometimes we can do some corrections afterwards to be able to simulate exactly from the same object that we care about, the posterior. Okay, so here I'm sort of making a connection to Metropolis-Hastings, and I'm doing that because in my other previous paper, we constructed a classification-based estimator of the likelihood ratio that we plugged into the Metropolis-Hastings. So I'm trying to sort of motivate the sort of generative approaches to posterior simulation, and I wanted to motivate it using two papers which have led to the paper I'm going to tell you about. So the second paper is also based on classification. Classification is obviously a task of distinguishing two data sets, right? In this case, we are generating fake data, and we are comparing it against true data, and then we're running a simulator who is, a classifier who is essentially trying to distinguish between them, and then based on the classifier, we construct a likelihood ratio estimator. So that was sort of kind of an attempt to come up with some sort of generative, not necessarily generative, but adversarial technique for Bayesian simulation. And that led to the paper I'm going to tell you about today, which is the GAN paper. So both the ABC and the Metropolis-Hastings had aspects of classification, but they didn't have the aspect of necessarily updating the generative model. So I'm going to tell you first about GANs in general, and then later on I'll explain how we tailored the GANs for posterior simulation. So GANs are construct from machine learning for simulating from likelihoods over complex objects such as images. So what the game, the method is actually based on a minimax game where we have two players. One of them is generator, denoted by G. The second one is a discriminator or critic, denoted by D. And they're playing this sort of minimax game where the generator is trying to trick the discriminator by generating data that increasingly more resemble the observed data. And the discriminator sets out to distinguish between the fake and real data. And as long as the discriminator can distinguish, the game continues. The game actually ends when the generator has perfectly learned to simulate data that resemble the true data so that the discriminator cannot tell. So the original formulation of the problem is the following. So we have this kind of entropy loss where we are comparing, we have a sort of generator generating fake data. So the GZ is the generation process, where we are essentially passing noise through a mapping. And this is where the generative, idea comes from. So the idea here is that any distribution can be sort of, represented as some sort of a mapping that, maps noise onto sort of, it's some sort of a mapping of, say uniform distribution or Gaussian distribution. So that's the generator. So generator will generate from the likelihoods by passing noise through a mapping G. And the discriminator is a essentially functional or some sort of classifier which assigns score 1 or 0, 1 for real and 0 for fake. And when you think about this formulation, it's obvious that the generator G star, so the G star D star is at the equilibrium. The generator essentially minimizes the Jensen-Shannon divergence between the true distribution and the generated distribution. And the Jensen-Shannon divergence, it turns out that in implementation of GANs, people have observed some difficulties. So they proposed Bayesian GANs instead. So in which case the generator minimizes the Bayesian distance between P0 and PG. And in our implementations, we focus on the Bayesian as well because it's more stable. But for sort of illustration purposes, I will focus on the entropy version because that gives us more insight into what the equilibrium looks like. So generative adversarial networks, they're really successful at creating realistic images. I will skip this one. That's a generative adversarial network of Veronica's. So the generator and discriminator, I want to just talk a little bit more about these two. So the generator is essentially passing noise through a mapping G to simulate from a distribution from the likelihood. So there's a reciprocal relationship between beta, which are the parameters of the network, and theta, which is the underlying parameter for the likelihood. So based on the feedback of the classifier, these coefficients get updated. So the generator improves at every step until it has completely, learned how to simulate from the true underlying sort of likelihood underpinned by the true parameter theta naught. So that's at the equilibrium. So the original GAN paper, right, has this nice cartoon which might be easier, which might be useful to understand the generator. So here we have the data Z, which is noise data, and then that gets transmitted onto through a mapping. So you could think of these arrows as the mapping. And the true data would be the black curve, and then the simulated data would be the green curve. So the simulated data is again map noise, right? And the discriminator is a score between 1 and 0. So whenever if the curves overlap, if the distributions overlap, the discriminator will be completely flat because it cannot tell which one is which. If the distributions do not overlap, then the discriminator will have, some discrimination powers. It will assign score 1 to the areas where the true data is more likely, right? And then 0 to the areas where the fake data is more likely. So it will be able to kind of distinguish between them. So the whole idea is that upon convergence, then the discriminator will be completely flat. So in reality, we, of course, I formulated the problem, the minimax problem, using expectations, but in reality, we will use averages. So there's going to be definitely approximation errors coming from using averages as opposed to expectations. But the good thing is that M is the number of simulated samples. We can choose that. It's a good idea to choose it, at least as large as N. But essentially, the classification problem is just a traditional classification. So we could pick a classifier such as logistic regression or deep learning. So the X is the real data, right? Sorry. X is the real data, and X tilde will be the fake data. And when the game ends, at the equilibrium of the discriminator can be represented as a sort of as a base classifier, essentially. So here we have it's a function of the likelihood ratio between the sort of simulated model and the true likelihood. So the simulated likelihood at the value theta and the true likelihood. So that essentially means that if we have a perfect discriminator, then we can express likelihood ratio through the perfect discriminator. So on the previous slide, this is the oracle discriminator, right, which can perfectly learn which is obtained at the equilibrium of the GAN game. So we can express the likelihood ratio in terms of this oracle discriminator. And that has been, used in my previous work using likelihood ratios inside of Metropolis-Hastings, and then using sort of classification to estimate the KL divergence. Okay, so that's about GANs, right? But now we want to come up with a simulator from the posterior, not from the likelihood. So how do we do that? So going back to the ABC reference table, we have samples from the joint distribution for theta and X. So we will be again playing a minimax game where we have a generator and discriminator. But right now we are contrasting two data sets which are both fake. So we'll be generating two sets of fake data. One of them will be arising from this joint distribution of theta and X. That's essentially the ABC reference table. And we'll be contrasting that against another fake data set with the same margin of X and different conditional for theta given X. And the conditional for theta given X is defined by a mapping, which depends on X because it's conditional, right? But it's a mapping that maps noise Z, right? So it's again a mapping, but compared to the previous case, now the mapping depends on X. So because you have one conditional distribution. So the key here is to really fix in the marginal of X, because in that case, learning the joint is equivalent to learning the conditional of theta given X. So when you play this minimax game, it turns out that at the equilibrium, you will learn the actual conditional distribution of theta given X. And the oracle discriminator will be, again, sort of a base classifier, which will depend on the ratio of the joint likelihood of the sort of the joint likelihood ratio. So it's a very kind of, I guess, simple observation that, if you do the GANs on the joint distributions and you fix the marginals, you learn simulate from the conditionals. So the whole algorithm can be summarized in a following table. So we simulate the ABC reference table. Then we simulate noise, right? And we construct for a given generator, which will be initialized at some, network. So G would be, say, deep network. And people construct two data sets, right? The first one is the ABC reference table. The second one is different, but it will have the same axis. So we take the axis from the ABC reference table, and then we will simulate another set of theta by passing noise Z through a mapping, right, which depends on the axis. And that's our sort of fake data set. Now, if the thetas are too far away from these thetas, right, then it means that this distribution is not close to conditional distribution of theta given X. So then we can feed these into a classifier and get feedback to the generator. The generator can improve and so on. So it iterates until convergence. And at the equilibrium, again, we expect to have learned the conditional distribution of theta given X. So in practice, what we do is we pick the classes for the generator and discriminator. In this case, we use the deep learning for both of them. And we train an empirical version of the problem with Wasserstein loss. So instead of looking at the entropy classifier, we use the Wasserstein loss, Wasserstein distance, and we replace the expectations with essential averages, where we have T simulations. So T pairs of simulated data from the one data set and another data set. So T is something we can choose ourselves. Because we are comparing fake data against fake data, we can make T as large as we can handle computationally. And once we have learned this mapping, which is essentially the parameters of the generator, once the algorithm converges, then we can plug it into the generator function. And then we can generate from the posterior by passing noise to a mapping conditionally on the data X0. So the data X0 is the observed data that's not used for training of the GANs, but it's used for filtering the noise at the end. So, we tried some sort of toy examples because this seemed like too good to be true to be able to kind of have two neural networks playing a game, and then all of a sudden we get stimuli from a posterior. We wanted to try a kind of simple yet tricky example. So this is an example of a two-dimensional, Gaussian. We have 4 observations, and the parameters you are trying to learn is the mean and the covariance, and the parameters are. So the covariance matrix is parameterized such that the parameters theta 3 and theta 4 are not identifiable. So we have multimodality in the posterior. The posterior can be computed in closed form in this case. So we can, compare the performance against the actual posterior. And here we looked at some ABC techniques using, say, Wasserstein distance, use sequential neural likelihood, which is related to our approach. The violet curve is the truth, and then the GAN sample will be the red curve. So we were quite, happy to see that we are capturing the multimodality, and it seems like we are also kind of concentrating close around the true parameter values. So that was reassuring, but at the same time, we can see that the posterior is not as sharply concentrated as it should be. And we thought that maybe there's a way to improve the approach further. So the problem with the GANs is that they don't use the training data, the observed data for training. They only use the observed data for simulation at the end. So what we wanted to do is maybe provide the GAN, provide GANs with better training data, which has many more simulations that resemble the true data, so that the GANs can learn around the true data X0. And one way how to do that is to improve the proposal distribution for ABC. So if the prior is flat, right, then the ABC training data set will have only very few X's that are similar to X0. And that's the problem, because we need a lot of X's that look like X0 in order to learn about the distribution conditionally on X0. So one way how to do that would be to perform a sequential approach where we refine the proposed distribution. So one idea would be to run this, to train this GAN, and then use the output as like a new prior for the next round. Obviously, it's a wrong prior, so we might have to correct for it afterwards using sort of reweighting. But that's definitely something we can do. So the two-step approach in this case would consist of running GANs twice. First, under a prior that's the original prior we want, and then once we learn some sort of pilot mapping, we can use the X0, right? We can conditional X0 and generate sort of samples from approximate posterior in this case and use it as a prior for the next round. So we again construct a reference table for ABC using this as a prior, but afterwards we have to reweight these samples because we used the wrong prior. So we can, if you can compute these weights, we can reweight the simulations easily. And it seems that the refinement is yielding distributions which are a little bit more concentrated and perhaps resemble the true posterior a little bit more closely. So that was one approach to refining the GANs. We looked at several simulations from the model. So this was kind of a toy example, but we wanted to make sure that the refinement is not just doesn't work only on one simulation. So we repeated a couple of times. I think it's 10 repetitions, and we look at the MMD discrepancy, and it seems that that the two-step refinement is improving the reconstruction consistently compared to the original GAN sampler. The SNL is also yielding a larger MMD distance. So assisting to ABC is also not as successful. So we like to think that in this particular simulation, the two-step GAN approach worked quite well. In terms of the tuning of the networks, we used kind of a default implementation of assisting GANs with, I think, 2 hidden layers and only 128 nodes in each layer. So we did not really attempt to optimize the network. Chances are that if we try to optimize it and try deeper or wider networks, we would get something even better. Okay, so that was a kind of demonstration on a toy example. I want to also talk a little bit about some statistical properties of this approach. So ultimately, we want to approximate a posterior conditionally on X0. So the whole idea behind the reweighting was that the GAN sampler in its original form essentially learns the mapping of, yields the posterior of theta given X for any X. But we don't want it for any X, we care about X0, right? So in the theory, we try to kind of quantify the total variation distance between the true posterior and then the approximated posterior conditional on X0, where we look at a typical distance when we take into account the data generating process. Okay, so there's some literature on GANs on their ability to approximate distributions. So we kind of leverage that literature and we tailored it to this conditional case. The bounds will essentially have 3 components. One of them will quantify the quality of the critic. Second one quantifies the quality of the generator. And then the third component is the complexity of these approximating classes. So regarding the critic, right, we want to make sure that the critic can distinguish sort of between the true model and the fake model. So essentially, we should be able to have a rich enough class such that we can approximate log posterior ratios quite closely. Then the generator, quality of the generator, again, we need to have rich enough generator class so that we can approximate the posterior distribution very well, right? So this class should be rich enough so that this log posterior ratio is small. And then the complexity measured by pseudo dimension means that we should not have this too rich of function classes. So on the next slide, I will have this class H, which is essentially kind of like a composition of deep learning or function classes. We need to make sure that this, this class is not too rich, which is a little, obviously these two goals go against one another. So coming up with a, deep learning architecture that kind of satisfies all these assumptions, we can only hope that there's some sort of equilibrium to be found. But if there was, deep learning mapping for architecture for the generator and discriminator, and if it turns out that these three terms go to zero, then we get essentially, vanishing total variation distance. So let me show you what the theory says. So beta hat t will be at the equilibrium of the game. So let me go back to both slides. The beta hat t is right here. So we have t simulations from the ABC reference table. So two fake data sets, right? And then it turns out that the posterior distribution approximated using this equilibrium point is not too far from the true posterior distribution in terms of total variation distance. So we can bound actually the expected total variation distance by these terms. So the first one will be implication of say the fact that we don't assume bounded likelihood ratios. If we did assume bounded likelihood ratios, we wouldn't need these two terms here. But we don't want to make that assumption, so that's essentially just our avoidance of that assumption. And then we have these three terms I described on the previous slide. So Pmax would be the complexity. So if we choose t large enough, chances are we might be able to send this guy, to zero. But again, we are not really looking into asymptotic, properties for n goes to infinity. We fix n, and we want to see if we can choose t large enough, such that this bound will be small. Now we have also prior concentration assumption, where epsilon n has nothing, like it's essentially just some sort of quantity. Which does not necessarily mean estimation like rate or anything like that. But we need to make sure that an epsilon n, if we looked into asymptotics, if you wanted to make sure that increasing sample size, things go to zero, we would need to make sure that an epsilon n squared will go to infinity. But in some sense, this epsilon, this assumption is kind of typical in Bayesian parametrics, but we don't like to think of epsilon n as epsilon as some sort of rate of estimation. So, that's a bound. Now we can argue, well, is there any architecture which will satisfy, for which this bound is going to go to zero, as we increase t, at least this portion of it. And we provided some intuition or some hints on how to construct it in the paper. But for now, it's just some sort of at least quantification of the discrepancy between the true posterior and estimated posterior. Okay, so I talked about how the GANs can learn the conditional of theta given x for any x. And if you wanted to improve the GAN sampler by tailoring it to conditional on x naught, right? Because we ultimately care about the posterior of theta given x naught. So we consider this one approach for refining the prior. So we could just sequentially apply this GAN technique to learn the prior, learn the prior and keep sort of refining it until a couple of times we tried it only in 2 steps, and then do posterior sort of reweighting using the importance weights at the end. So that's one possible approach. There is another possible approach to incorporate the actual observed data in the training process, not through the proposal, but through the actual training mechanism. So we thought about another way of refining the GAN sampler by considering sort of variational Bayes approach. So in variational Bayes approach, you're essentially trying to come up with an approximation to posterior such that we maximize the lower bound to log marginal likelihood. So we want to choose some sort of posterior approximation class indexed by beta again, which will be, giving a large lower bound to the marginal likelihood, log marginal likelihood. And in implicit variational base, this class is defined implicitly through a mapping again. So this is the generative aspect of variational base, where we essentially just want to learn a mapping, such as deep learning mapping indexed by some coefficients beta, which will after passing noise through it, will provide approximate samples from the posterior, right? So it's a very similar idea, very similar goal, but the objective function is different. The way this push forward mapping will be trained is different. So when you look at the lower bound to the log marginal likelihood, you can write it as a minus Kullback-Leibler or divergence between the true posterior, conditional on x naught, right, and the approximate posterior. And obviously, the true posterior is not known, but so that's why we cannot really, evaluate this. But if we could augment this this conditional by into a joint distribution, then we can estimate actually the Kullback-Leibler divergence between the joints, and then we could actually try to optimize that. So the whole idea is that if we essentially look at augment the conditional with a joint, and we keep the marginals the same, we can again sort of learn the actual conditional distribution. So a couple of slides ago, I showed you the sort of classification track or likelihood ratio track, where if you contrast two joint distributions which have the same marginal but different conditional, so if we classify or try to discriminate between those, the oracle discriminator will actually have learned the ratio between the two joints. So that's the whole idea, right? And then after observing that, we can essentially rewrite the variational lower bound in terms of the oracle discriminator of the joint. So this lower bound, which depends on the posterior we don't know, we can essentially rewrite it as the oracle discriminator, which we can estimate. Okay. So this oracle discriminator is essentially just classifier, right? We can estimate it using a classification on two fake data sets again, which is essentially the same approach as in the GANs. So the discriminator will be the same, but the generator will be different, because the generator now tries to maximize lower bound to marginal likelihood. So the objective function for the generator is different and does depend on x naught. So in some sense, the generator will be trying to find a maximum of this function, which depends on x naught, which is different from the previous GAN approach, because the vanilla GAN sampler has never seen x naught. It only has seen fake data. So that's why we thought that this variational approach might yield a little bit better reconstruction, because it's trained on x naught. Okay, so there's just a summary of the algorithmic steps, but I want to show you demonstration on a data set. So we considered kind of a quintessential likelihood-free data set from ABC literature, Ročková model, which has 4 parameters. It describes population dynamics where predators interact with prey, and the rate at which the predator is being born depends on theta 1. Theta 2 describes the rate of predator dying, and theta 3 would be for prey being born, and theta 4 for prey dying. And the Ročková model is easy to sample from, but there's no expression for the likelihood. So it's an ideal candidate for ABC style techniques. Here is just demonstration of what the data look like for different settings of parameters. So if we change the parameters slightly, we may obtain very different trajectories. right, where the predators may take over the prey. There's only a slight change in the second parameter, which may create a very different dynamic. So this means that if we run a classifier, right, the classifier should pick up on these differences. What we will do is, right now I want to show you two demonstrations. One of them has multiple copies of the time series, because here we have 20 time series for predators and prey, each of length 200. So in the first demonstration, we will have multiple copies of the time series, and in the second one, we'll have just one time series. And we have these true values which we want to recover using a simulation approach. So we will try ABC based on some sort of summary statistics concern, that we found in the literature. So this is the kind of default approach. And then we used also the classification-based estimator of the likelihood. So this was in our previous paper, Metropolis-Hastings. It turns out that the ABC discrepancy is somewhat minimized at the true value for one of the parameters, keeping all the other parameters fixed. You can see that the likelihood is kind of maximized around the true value. So both of these approaches might have some, there's hope that we might be able to recover the parameters, even though the problem is quite complicated because the likelihood is spiky. So here we have theta 1, theta 4. This would be the kind of heat map of the estimated likelihood. And the range for which the likelihood has support is very narrow. So if you were to assign a prior on a unit cube, chances are that the probability of hitting this region is fairly small. So ABC approach might require very long reference tables. So there's also hope for us to kind of leverage the sequential approach where we can refine the prior as we go. But we wanted to make things kind of simple for ABC. So we narrowed the range for this theta 1, theta 4. We ran ABC for 100,000 simulations, keeping the first one of the best 1% samples for posterior reconstruction. It's not a matter of choosing the number of simulations because it seems like the summary statistics do not have enough information about theta 2 and theta 3. So that was, just I guess the nature of the basic ABC with summary statistics. It doesn't just not made for this problem. Whereas the Metropolis-Hastings, which is the likelihood-based, the classification-based estimator of the likelihood ratio, seems to be capturing these parameters much better. At least it learns around, about theta 2 and theta 3, yielding sort of tighter, credible intervals and less bias compared to the ABC. So that was, very assuring. This is not a GAN approach. This is from the previous paper on Metropolis-Hastings. But there was one thing that we needed for this approach, and that's multiple copies of the time series. So we had 20 copies so that we can run the classification approach, right? Now, when we have only one time series, we cannot apply any of those techniques from my previous two papers. So the Metropolis-Hastings and classification-based ABC, they just need multiple copies. So for n equals 1, we can't really do that, but we can apply the GAN approach. So because that doesn't require sort of independent observations. So we trained the GANs on this data set, and you can see the reconstruction here, where we have the true values marked by the vertical lines, and then the original B-GAN sampler will be the red curve, and refinement using two-step. The two-step refinement is in blue, and then sequential narrow likelihood is also doing really well. And then we have the, I believe that, yes, so this would be the variational refinement here. So the variational refinement and the two-step refinement seem to be improving on the original, which is vanilla GAN approximation. Okay, so this is just a summary of 10 repetitions. So just simulation study with 10 repetitions. where we are able to show that either one of these two refinement approaches will yield better reconstruction than the original GAN approach. And we were really happy to be able to apply sort of this technique for sort of one realization of time series where, you know, other techniques might be more challenging. So I think that this approach has a great potential. Again, we haven't really tried to optimize the networks. We used kind of a default implementation. So I think that with the rise of, you know, deep learning and generative models, there is hopefully potential for this, for more like better architectures and to be fed into this framework so that we can, you know, get stable sort of deep learning architectures to approximate posteriors. I think that there's a huge potential here, and we tried several toy examples, and you know, I'm hopeful that this approach will eventually take off, and people will be comfortable using sort of generative models for posterior simulation. So with that, I would like to thank you very much for your attention. I know that I ended a little early, but at least we have some time for questions.